Go.
Hi, I'm Corbin Yates. I'm a mechanical engineer. I graduate in summer of 2025. My interest in this project, well, first to start, we did a model car aerodynamics and Vortex generators. My personal interest is we need cars to go just about everywhere that we need, and I wanted to dive in and learn more about aspects of a car, and aerodynamics is something that interests me and something that I wanted to learn about.
My name's Adam Meyer. I'm a senior 2 mechanical engineering student, and my personal interest in this project is actually before I wanted to become a full-time mechanical engineer, I actually had plans to study aerospace engineering and mechanical engineering, so this gives me a good aspect of studying that aerodynamical aspect. And like Corbin said, our project is on the aerodynamics of a car. So now, for a little introduction of what our project is, the purpose of our experiment was to find and measure the coefficient of drag and lift on a model car, as seen here in this Porsche 911 GT2 RS. We're going to measure the coefficient of drag and lift around the car, and additionally, we added Vortex generators onto the car to see their impact on the coefficient of drag and lift. And this gave us also a better understanding of the basic concepts of fluid dynamics, such as pressure differentials, manometers, air density, and vortex generators.
The main principles of fluid mechanics in this project is the flow over an immersed body, our Porsche 911. With bodies that are immersed in a fluid due to the no-slip condition, which is where the air actually sticks along the body of the car. This results in a viscous force along the acting body with the additional pressure distributions along the body. The resultant causes restaurant forces of lift and drag. The lift with the downforce on the car and the drag of the air on the car.
So now for this project, some of the different things that we used in it were a digital manometer, lift and drag measurement device, the wind tunnels as seen here, a 1/24th model Porsche GTRS, some brass tubing, some plastic tubing here at the end. Additionally, we used some epoxy to put into the brass fillings onto the car to secure them in place. Additionally, we used a mounting arm, as seen right here, which was actually in the lift and drag measurement device, which we used to measure the force. Additionally, for building actually the model, we used a power drill, a thermometer to measure the temperature in the project, a Dremel, a drill bit obviously, another drill bit, and the 4 Vortex generators as seen there, and some super glue and some sticky notes to measure our different tubes and secure them in place.
So the procedure that we were following, to start, we had to get our model car all set up, drilling holes, as he said, and then actually mounting it onto our stand, which we had a different table under here. We would slide our car on the mount down, and it would hold it into a steady position. After that, we had to feed our tubes into a hole that was at the bottom for our readings with the digital manometer. With the digital manometer, we had different various readings. We had all of these labeled and we put the manometer on them to get our different stagnation and static pressure readings.
Additionally, we changed the speed of which the fan was operating at and the temperature that the air was through the tunnel to measure our different properties and get us some results.
Yes.
Here's a quick video demonstration of us in the lab, as you can see here. So here's our car in the stand there. We would clip on the tube of either a static or a stagnation point into the digital manometer, and we would get a reading. This was in kilopascals. And then we would switch throughout the tubes, this was one result where we kept the fan speed constant, and or the temperature constant. We'd go through and we'd measure each point and record it on our Excel sheet. And then we would go through and then have to either wait on changing the fan speed or we would change the air temperature. So now, as I said, when building the car, we created 4 different static points along the car and 1 stagnation point here, as seen here in the front of the car. So what was done is we drilled actually holes, as you can see right here, into the car. And then underneath, we implanted these brass tubings and we secured them in place directly through with the tube by putting a drill bit in to hold it in place, and then we epoxied these in place. So then we super glued each tube into the static points and one to the front for the stagnation point here, and drilled holes through the bottom so we could run them out through the car.
The car setup, as mentioned before, we had it in the wind tunnel with the tubes feeding out through this hole for the manometer to take the readings of the pressure of static and stagnation points. This is without the Vortex generators. We had to take it out, apply the Vortex generators, and repeat our measurements.
So now before we get into our data and our results, we just want to go over some basic calculations that were used throughout the lab that we learned in class, actually. And the main equations that were used were the lift coefficient equation and the drag coefficient equation. So these both used either the force of lift or the force of drag. Additionally, the air density, which we had to measure, the velocity, which we measured from the speed, and the area of the car, which is not exactly the area, and we'll show you that a little bit later on. So now to get into some of the data that we were seeing, as seen from those equations, when this is all data concerning the drag along the different points of the car and resulting in the coefficient of drag as fan speed increased, we saw overall a decrease in the coefficient of drag, which makes sense when we relate it back to those equations because the fan speed relates to the velocity of the air in the tunnel, and that's in the denominator of the equation. So as that increases, we would expect a smaller result for the coefficient of drag, which is what we've seen throughout all of our points.
And as you can see here, our coefficient of lift versus our fan speed, as the speed along the hood increased, we saw more lift as we increased the speed. Same thing for the roof. The rear windshield was in a little bit different scenario because we had a little flange here that would throw the wind off of our reading pressure. Therefore, the lower it was, the less it would throw the wind off, and we would actually get a better measurement. And same thing for the rear windshield. As the lower amounts of speed, the air would travel along the car, and we would get a really good reading for it. And with the speed picking up, it would kind of just fly off, and we want to get that great of a reading.
And just to note that these are all negative results, so this is actually downwards force on the car.
Yes.
Additionally, we ran two different sets here. We ran one where we kept temperature constant and we increased the fan speed. That was what you just saw. Now in this set, we kept the fan speed constant and we increased the temperature. So now in this case, we would see, in each scenario, we saw an increase in the coefficient of drag, and this makes sense as increasing the temperature actually decreased the air density, which is, as we've seen, is in the denominator of the equation for the coefficient of lift and drag. So this resulted in an increase in the drag on the car, or the coefficient of drag on the car.
And just as Adam just stated, with the air density being in the denominator of the car, we would have less lift. And as you can see here with the coefficient of lift versus the temperature, as we were at a lower temperature, we would have less lift of the downward force compared to having a higher speed along every single point.
As we've seen right there, the simple equations that we use to process this is the density from there as seen with it being in the denominator, and the equation actually for the velocity that we use to calculate our data.
Going on with the car setup, we had to find the area of the car. So what we did is we had the car stationed and had a flashlight, as you can see, to cast a shadow along the back, and did a little bit of a trace to find our area of 0.0099 meters squared.
This is not simply just the cross-sectional area. It's actually almost an imitation of the air that would run across on the car. Yes. And that's why we use a flashlight to imitate this on a dry erase board. So now that we ran through our data on what happened without the Vortex